Welcome back. Last time in the series we covered robot design, how to plan, build, and attach a robot that can actually get out of the table. Today we're picking up where that left off, how to program that robot to drive and turn precisely, using the gyro sensor and a control algorithm called PID. So what are we actually doing today? Last time we covered robot design, the base robot, and the attachments it carries. Today we shift to programming, making that robot move exactly where you point it. Almost every mission comes down to two skills: driving straight to an exact distance and turning to an exact angle. Gyro PID is how we do both reliably. It uses the gyro sensor built into the hub to constantly check the robot's heading and correct for drift in real time while it's moving. We're also going to cover the speed curve that shapes power over a move, a way of ramping power and tapering it back down smoothly instead of slamming from a dead stop to full power. This is why it matters. Missions score based on the robot ending up in a specific spot, facing a specific way, not just somewhere else. And here's the problem. Motors never perform identically, and your battery level and the table's friction drift over the course of a match are gonna be different. Fixed power alone can't compensate for that. A robot that drives on raw power with no correction will drift a little differently every single run. Since FLL needs to be extremely precise, so many different measures are taken to do that. For example, trying to run your robot at the same battery power every time, or at 100% power every time, or cleaning your wheels, and so forth. Gyro PID actually helps the program understand and accord to that. The robot allows the robot to notice its drifting and correct itself instead of relying on a perfect build and perfect conditions. This is what makes complex multi-step missions possible without the robot solely wandering off a mission model. Fair warning, this is precision work. Expect to spend real time tuning constants, not just placing the blocks once and walking away. Let's look at the 5 pieces we'll walk through today. First, PID control, the core idea behind steering correction we'll use today. We'll build it up from scratch, covering all 3 terms it is used for: proportional, integral, and derivative. It happens to be the same essential idea line following uses as well, just with a different sensor feeding it. This is important since we will mainly be going over the gyro aspect, but if you can incorporate the same idea into line following, it would be great, since judges want to see line following. It is something that, even though it may not seem necessary for your game logic or your game theory, it is an important part of robot design that judges like hearing about: line following or stopping at a line. At some point, you're going to need to use line detection using these light sensors, and you should be able to incorporate the PID control that we explained today into that. Second, the gyro sensor itself, which is specific for the gyro PID, what it reads and how. Third, we'll cover the speed curve that ramps power smoothly, and then 2 main events: gyro PID for driving straight and gyro PID for tuning. Everything after that is the first idea builds on top of, so don't skip ahead in your head. They stack. So before we can use the gyro to correct our heading, we need one core idea that everything else today is built on: PID control. PID is a feedback control algorithm that basically takes a look at how far away you are from your target, which is your error, and based off of that, adjusts your mechanism to move to your target smoothly without overshoot. PID stands for proportional, integral, and derivative. 3 different ways of looking and adjusting your error. They get added together into one final correction. Let's take them one at a time. Start with error. Your target value minus your current value. If you're right on target, error is 0. If you drifted away, error grows, positive one direction, negative the other. The P term, proportional, reacts to how far off you are right now. You multiply the error by a constant of proportionality, the Kp, and that's basically your proportional correction. The reason you need to multiply a gain to your error directly is so you can tune how fast the robot reacts to how far off you are. Because the error is not scaled to the mechanism that you're using, and therefore you need some way to scale it so that it doesn't completely overshoot. A small error gives a small correction, and a big error gives a big one. The idea is it moves proportionally to the error. On its own, though, proportional control has a weakness. It can leave a small steady error uncorrected, because as the error shrinks, so does the correction. Sometimes down to less than what actually takes to finish the job. That's where the I term, integral, comes in. Integral keeps a running total of the error over time, adding a little bit more each loop, and multiplies that by a total by ki. If a small error lingers loop after loop, that running total builds up, and the correction keeps growing until it's finally enough to close the gap. Then there's the D term, derivative. Derivative basically looks at how fast the error is changing. Basically getting the difference between the loop's error and the last loop's error multiplied by the kd. If the error is closing in fast, derivative pulls back on the correction so you don't overshoot. It's what smooths the response out and helps prevent that back and forth wobble. Put all these three together and you get your final correction. Kp times error plus ki times the running total of error plus kd times the change in error. Today, current is the gyro's heading reading. It's worth knowing the same PID idea is also how line following works. There, current comes from the light sensor's reflected light intensity compared to the threshold value that marks the edge of the line, instead of a heading compared against an angle. It's usually around 50 if it's a 0 to 100 light intensity reading. It is important that everyone understand this well so that when asked in judging, you can present it with confidence. Now for the gyro sensor. The gyro sensor lives right inside the hub. No extra wires or ports needed. It measures three things: pitch, roll, and yaw. Yaw is the one we care about. It's a robot's rotation left and right around a vertical axis, which is exactly what heading means on a flat table. Pitch and roll matter more if your robot tips or rocks, less useful for us on a flat FLL mat. One habit to build early: reset the gyro angle once at the start of your run so that 0 means something consistent. Every move after that references to the same 0 point. You should probably need to have a calibration process on a button press before your run starts. That will probably help it. And note that heading can drift a little over a long match. That's normal. It's exactly why we correct continuously instead of just checking once at the start. Another approach is just to zero your gyro before every movement or every turn, so that instead of keeping an absolute position of your angle, you position it as a relative angle heading. Before we combine our gyro correction with movement, let's talk about how we control speed itself, because this matters just as much as the correction math. If you jump straight into full power the instant you start moving, you can imagine that your wheels will slip on the mat, throwing off your heading before you even started correcting for it. If you slam to a stop at full power when you hit your target, you overshoot past your target distance or your target angle. Think about it when driving or riding in a car. If the car suddenly stops, or suddenly the brakes are applied, the car will slide or even flip. That's why you slowly apply the brakes, adding slight deceleration. The fix for us is to shape the power with a curve based on the percent of the move you have completed. Power stays low near the start, climbs up toward a peak around the midpoint of the move, and that's where you get your fastest and most efficient travel, then tapers down as you approach your target. And instead of tapering all the way to 0, it is floored at a small minimum power, so the robot still has just enough to finish the move instead of stalling out short of it. Picture it on a graph. Power on one axis, distance remaining on the other. And the shape is a smooth curve, low at both ends, peaking in the middle. The important detail is what you base that percent done number on. Use how far you've actually traveled, or for a turn, how much air remains, not time. Time doesn't account for a low battery or a stickier table. Distance and remaining air do. And this exact same curve works for both of today's topics, driving straight and turning, just applied to a different measurement. One more thing worth knowing up front. The exact numbers here, how much the curve peaks, how big your floor power needs to be, all that have to be tuned for your specific robot. We won't walk through that tuning process today, just know that it's going to be part of the deal. Here's the first of our two main topics. When you drive in a straight line, record your starting heading as the target. Usually that's just 0. Then every single loop while the robot is moving, read the current heading from the gyro. Subtract the current from the target and you get your error, Positive if you drifted one way, negative if you drifted the other. Now compute your full PID correction. Multiply that error by Kp for the proportional piece. Add Ki times the other. Multiply Ki times the running total of the error for the integral piece, and add Kd times the change in error since the last loop for the derivative piece. Here's the key move. Add that whole correction to one motor's power and subtract it from the other motor's power. That small speed difference between the two sides is what steers the robot back towards straight, without stopping or turning sharply. Because this loop runs many times per second, you get tiny corrections happening constantly, long before any drift becomes visible to the eye. Now let's combine that with a speed curve from a couple slides ago. The base power for both motors before steering correction comes from that curve, low at the start, climbing near the peak, near the midpoint of the distance, and tapered back down as you near your target distance. The gyro correction gets added on top of that base power, one side up a little, one side down a little, so it steers without meaningfully changing your overall speed. Loop the whole thing, read heading, compute error, and the full PID correction. Compute the current base power from how far you have traveled, set both motor powers, and repeat. Once you hit your target distance, stop the loop and bring both motors to 0 together. Let's look at what this actually looks like in real code so you can see these ideas aren't just theory. This is a My block, which is a custom reusable block that packages everything we've covered for driving straight. Think of it as a function. At the top, it takes in a target heading, a distance in rotations, and a minimum power floor. Ideally, you would program this so you do your distance in degrees of your motor rotation instead of the amount of rotations, because it's slightly more accurate. But in this example, it's using rotations. The setup at the start resets the gyro to 0 and zeroes out both drive motors' position counters. Then initializes the P, I, and D gains and clears out any leftover error values from the last time it ran. The main loop keeps running until the drive motor's position reaches the target distance by checking the amount of rotations that it ran, and if it's greater, and converted from rotations into degrees. Inside that loop, it computes the error, then works through the proportional, integral, and derivative pieces one at a time, and adds them together into a single steering correction. For speed, just like we covered, this code uses a curve based on % of the distance completed. It peaks in the middle and tapers at both ends with a floor, so it never drops too low near the start or the finish. Finally, it steers with that PID correction and powers the drive with the speed curve, looping the whole thing until the distance target is hit, then stops. Now that we have covered PID gyro driving straight, we can move on to turning. The setup looks almost the same, but a couple things do flip. Your target heading is no longer 0, it's whatever angle you actually want to turn to, say 90 degrees. Error is still target minus current, but now that error starts large, close to the full size of your turn, and shrinks towards 0 as the turn completes. Run that error through the full PID formula, Kp times error plus Kp times the running total of error plus Kd times the change in error. And that sum is your turn power. Here's the difference from driving straight. That whole PID sum is the power. There's no separate base power added on top of it. And instead of a small speed difference between the two motors both spinning forward, you apply that power in opposite directions, one motor forward and one motor backwards, so the robot pivots in place. One nice side effect, because the error naturally shrinks as you approach a target, the turn power shrinks right along with it. The turn slows itself down automatically as it finishes. Just like with driving straight, we still want the same speed curve here. Two reasons. A floor power so the turn doesn't stall out completely once the error gets very small, and a curve so it doesn't slam to full power the instant the turn begins. Base % complete on how much error remains, not on time. A bigger requested turn should still get a real peak in the middle instead of finishing before the curve ever ramps up. Loop it in the same way. Read heading, compute turn power from the full PID sum and the speeds, curves, floor, and taper. Set the motors in opposite directions and repeat. One more detail that saves a lot of headaches. Don't stop the instant error hits exactly 0. Check that error stays in a small tolerance for a few loops in a row before you call the turn done. That settling check keeps leftover momentum from carrying the robot past the target after you've already stopped correcting. Let's put straight vs turning side by side. It's easy to blur them together. So for driving straight, your target is your starting heading, usually 0, and the error means how far you've drifted left or right. Both motors spin forward, just at slightly different speeds. PID together add up to a fine steering correction added on top of your base power, and the speed curve shapes that base forward speed on percent of distance completed. For turning, your target is the angle and you actually want to reach, and the error means how many degrees are left to turn. The motors spin in opposite directions to pivot in place. PID together are the driving power for the turn, and the speed curve's job shifts to providing a floor and a ramp up underneath that shrinking power. Same underlying math, two different jobs. A few practical tips before I wrap up. Tune KP, KI, and KD separately for driving straight and for turning. They almost always need different values. Don't assume one set of constants works for both. If KP is too high, you'll see oscillation. The robot wobbles or overcorrects back and forth instead of settling. If it's way too low, the robot corrects too slowly and drifts noticeably before it straightens back out. Watch KI too. If it's too high, you get a different kind of overshoot called integral windup. That accumulated error keeps pushing the correction even after you're already back on target. And watch KD. If it's too high, the response gets too jittery because it's reacting to even the tiny bit of noise in your error reading, not just the real trend. When you're tuning, change one constant at a time and retest. Don't adjust your ramp speeds and your PID constants in the same run. You won't know which change caused what. And last thing, reset the gyro once right at the start of your match run, and maybe even between every individual move or not. Both of them are possible, but make sure that your heading reference stays consistent across the whole run. Finally, there's a key thing to remember. When designing your spike robots, you have two motors, and they're going to be facing different directions. But if you orient these in a certain way, these motors aren't actually rotating in the same direction if you want your robot to drive straight. Therefore, when applying these speeds, you're going to have one speed positive and one speed negative. Now, that's driving and turning with gyro PID. Next time in the series, we're moving on to growing your team's core values. Thank you for watching. That's it for today. Go get your gyro correction tuned, start with driving straight, then move on to turning once that's solid. And don't be surprised if your first KP value isn't your final one. I'll see you in the next video.